The Hammer Mill Company produces paper for laser printers. Standard paper width is supposed to be 216 millimeters or 8.5 inches. The actual width is a random variable that is normally distributed with a known standard deviation of 0.023 millimeters. The standard deviation reflects the manufacturing technology currently in use and is considered known from long experience with this type of equipment. The standard deviation is small due to the company's considerable effort to maintain precise control over paper width. However, variation still arises during manufacturing because of slight differences in the paper stock, variation in the rollers and cutting tools, and wear and tear on the equipment. The cutters can be adjusted if the paper width drifts from the correct mean. Quality control inspectors frequently run tests on samples to make sure the cutters are in alignment. Cutting the paper too short or too long is a problem. In one example, a quality control inspector chose 50 sheets at random and measured them with a precise instrument showing a mean width of 216.007 millimeters. Using a 5% level of significance, does this sample show that the product mean differs from the specification? Okay, so we have information or data that's been gathered by a quality control inspector, and we want to run a test. For this machine, this is going to be a test on averages, the average paper width, and it's going to be a two-tailed test. We are going to assume that the machines are working properly, so our population average width of the paper is 216. We may have evidence here that that there's a problem and that the real average is not 216. So in step 1, we'll set up our null and alternative hypotheses. In step 2, let's look at our sampling distribution. And we are assuming that the null is correct. So the center of the distribution should be 216. The standard error, we have the population standard deviation. So we will calculate this as 0.023 over the square root of our sample size at 50, and we get 0.00325. This is a two-tailed test, and with alpha equal to 0.05, I'm going to split that. 0.025 on the upper and lower ends, establishing our decision lines and our critical values at negative 1.96 standard units to the left, 1.96 standard units to the right. So our rejection rule, we will reject H sub 0 if our test statistic is less than negative 1.96 or it is greater than positive 1.96. Step 4, we'll calculate the test statistic on our sample average of 216.007 to see how far away that is from 216 in standard units. And that value turns out to be 2.15 standard units to the right. And with our level of significance, we are far enough away from center to say with confidence that the null hypothesis is incorrect. So step 5, we're going to reject H sub 0. Since 2.15 is greater than 1.96, and conclude then that the machines need adjustment. Now let's go ahead and run this test using a p-value. Now we have 2.15 as our test statistic, and that is greater than 1.96. So our sample average at 216.007 is somewhere up here on the top end of this distribution. We are going to calculate the probability of getting anything less likely than this on the upper end. And to do that, I need to go to the standard normal table with my 2.15. And remember, the standard normal table will give us the probability to the left of the 2.15. So to get this upper end, I'm going to have to take the table value away from 1. The table value for 2.15 is 0.9842. And since this is a two-tail test, I want to compare it to our original level of significance at 0.05, so I'm going to multiply this by 2, and that is my p-value. This is equal to 0.0316, and 0.0316 is less than 0.05, so I reject h sub 0 using the p-value method. Now, the whole hypothesis test here is set up so that we can avoid type 1 error. Type 1 error is rejecting the null hypothesis. In this case, the null hypothesis is saying that the machines are working well, cutting that paper on average to 216 millimeters. Type 1 error would be saying that that is wrong, but it turns out in reality it's actually right. We don't want to make a type 1 error. We don't want to reject the null hypothesis when it is true. That would mean that we are trying to fix these machines when they don't need fixed. And in some cases, if we try to shut them down and make a realignment, we could be losing time, product, and money. So we don't want to make a type 1 error. When we set alpha equal to 0.05, we are saying that we want no more than a 5% probability of making a type 1 error. In step 2, we set up the sampling distribution, assuming that h sub 0 is true. We draw our decision lines at the z locations negative 1.96 and 1.96. If h sub 0 is true, only 5% of the sample averages that we would get from samples of size 50 are beyond these two lines. 95% of the sample averages are inside of these two lines. So I'm going to go ahead and put that in green. 95% of the sample averages are inside our two decision lines if the null is true. So if h sub 0 were true, there is a 95% chance of getting a value inside of these lines and a 5% chance of getting a value outside of these lines. So when we don't get a value inside, but instead get a value such as we got, it sheds doubt on h sub 0 being true. Enough doubt that we can go ahead and reject h sub 0 and be confident that the machines do need alignment or fixed. The p-value is nice in the sense that it not only runs the test for us to determine whether we can have that confidence to reject, but it also gives us the strength of our evidence.